Slump occurs when material slips downslope en masse along a curved surface of rupture. It is an example of a rotational slide. Earth flows frequently form at the base of the slump. Figure 12.12 Slump. Slump commonly occurs because a slope has been oversteepened. The material on the upper portion of a slope is held in place by the material at the bottom of the slope. As this anchoring material at the base is removed, the material above is made unstable and reacts to the pull of gravity. One relatively common example is a valley wall that becomes oversteepened by a meandering river. Figure 12.13 provides an example in which a coastal cliff has been undercut by wave action at its base. Slumping may also occur when a slope is overloaded, causing internal stress on the material below. This type of slump often occurs where weak, clay-rich material underlies layers of stronger, more resistant rock such as sandstone. The seepage of water through the upper layers reduces the strength of the clay below, resulting in slope failure. Waves undercut the base of the steep slope, making it unstable. Figure 12.13 Slump at Point Fermin, California. Rockslide and debris avalanche. Rockslides occur when blocks of bedrock break loose and slide down a slope. If the material involved is largely unconsolidated, the term debris slide is used instead. After the initial sliding stage, the material can break up into a chaotic debris avalanche. Such events are among the fastest and most destructive mass movements. Usually rockslides take place in a geologic setting where the rock strata are inclined, or where joints and fractures exist parallel to the slope. When such a rock unit is undercut at the base of the slope, it loses support, and the rock eventually gives way. Sometimes a rockslide is triggered when rain or melting snow lubricates the underlying surface, to the point that friction is no longer sufficient to hold the rock unit in place. As a result, rockslides tend to be most common during spring, when heavy rains and melting snow are most prevalent. These rapid movements are classified as translational slides, in which the material moves along a relatively flat surface with little or no rotation or backward tilting. Figure 12.14 Rockslide. As mentioned earlier, earthquakes can trigger rockslides and other mass movements. There are many well-known examples. On August 17, 1959, a severe earthquake west of Yellowstone National Park triggered a massive slide in the canyon of the Madison River in southwestern Montana. In a matter of moments, an estimated 27 million cubic meters of rock, soil, and trees slid into the canyon. The debris dammed the river and buried a campground and highway. More than 20 unsuspecting campers perished. Heavy rains and melting snow, rather than an earthquake, triggered another major rockslide, a debris avalanche in the Yellowstone region. The legendary Gros Ventre rockslide occurred not far from the site of the Madison Canyon slide, 34 years earlier. The Gros Ventre River flows west from the northernmost part of the Wind River Range in northwestern Wyoming, through Grand Teton National Park, and eventually empties into the Snake River. On June 23, 1925, a massive rockslide took place in its valley, just east of the small town of Kelly. In the span of just a few minutes, a great mass of sandstone, shale, and soil crashed down the south side of the valley, carrying with it a dense pine forest. The volume of debris, estimated at 38 million cubic meters, created a 70-meter-high dam on the Gros Ventre River. Because the river was completely blocked, a lake was formed. It filled so quickly that a house that had been 18 meters above the river floated off its foundation 18 hours after the slide. In 1927, the lake overflowed the dam, partially draining the lake and resulting in a devastating flood downstream. Why did the Gros Ventre rockslide take place? Figure 12.15 shows a diagrammatic cross-sectional view of the geology of the valley. You will notice that the sedimentary strata in this area dip 15 to 21 degrees. Underlying the bed of sandstone is a relatively thin layer of clay, and at the bottom of the valley, the river had cut through much of the sandstone layer. During the spring of 1925, water from heavy rains and melting snow seeped through the sandstone, saturating the clay below. Because much of the sandstone layer had been cut through by the Gros Ventre River, the layer had virtually no support at the bottom of the slope. Eventually, the sandstone could no longer hold its position on the wetted clay, and gravity pulled the mass down the side of the valley. The circumstances at this location were such that the event was inevitable. This massive slide occurred on June 23, 1925, just east of the small town of Kelly, Wyoming. Smart Figure 12.15 Full Alternative Text Description. Smart Figure 12.15 Gros Ventre Rock Slide. Watch tutorial, Gros Ventre. Debris flow. Debris flow is a relatively rapid type of mass movement that involves a flow of soil and regolith containing a large amount of water. The La Conchita debris flow is one example. Debris flows are sometimes called mud flows when the material is primarily fine-grained. As you will see, debris flows are a particular problem in semi-arid mountainous regions and on steep volcanic slopes, where they are called lahars. Because of their fluid properties, debris flows frequently follow canyons and stream channels. In populated areas, debris flows can pose a significant hazard to life and property. During the week of September 9 to 13, 2013, residents in and near Boulder, Colorado, received a harsh reminder of the dangers posed by debris flows. During that 5-day span, nearly continuous rainfall triggered numerous flash floods and more than 1,100 debris flows in an area, covering more than 3,400 square kilometers. Figure 12.16 Debris flow in the Colorado Front Range. Debris flows in semi-arid regions. When a cloudburst or rapidly melting mountain snows create a sudden flood in a semi-arid region, large quantities of soil and regolith are washed into nearby stream channels because there is usually little vegetation to anchor the surface material. The end product is a flowing tongue of well-mixed mud, soil, rock, and water. Its consistency may range from that of wet concrete to a soupy mixture not much thicker than muddy water. The rate of flow, therefore, depends not only on the slope but also on the water content. Dense debris flows are capable of carrying or pushing large boulders, trees, and even houses with relative ease. Debris flows pose a serious hazard to development in relatively dry mountainous areas such as Southern California. The construction of homes on canyon hillsides and the removal of native vegetation by brush fires and other means have increased the frequency of these destructive events. Moreover, when a debris flow reaches the end of a steep, narrow canyon, it spreads out, covering the area beyond the mouth of the canyon with a mixture of wet debris. This material contributes to the buildup of fan-like deposits, called alluvial fans, at canyon mouths. The fans are relatively easy to build on, often have nice views, and are close to the mountains. In fact, like the nearby canyons, many have become preferred sites for development. Because debris flows occur only sporadically, the public is often unaware of the potential hazard of such sites. Lahars. Debris flows composed mostly of volcanic materials on the flanks of volcanoes are called lahars. The word originated in Indonesia, a volcanic region that has experienced many of these often destructive events. Historically, lahars have been some of the deadliest volcano-related hazards. They can occur either during an eruption or when a volcano is quiet. They take place when highly unstable layers of ash and debris become saturated with water and flow down steep volcanic slopes, generally following existing stream channels. Heavy rainfalls often trigger these flows. Others are initiated when large volumes of ice and snow are melted by heat flowing to the surface from within the volcano, or by the hot gases and near molten debris emitted during a violent eruption. An eruption in April 2009 of this volcano on Alaska's Kenai Peninsula sent lahars down the valley of the Drift River. The dark color of the lahar contrasts sharply with the surrounding snow-covered landscape. When Mount St. Helens erupted in May 1980, several massive lahars were created. The flows and accompanying floods raced down the valleys of the north and south forks of the Toutle River at speeds often in excess of 30 kilometers per hour. Fortunately, the affected area was not densely settled. Nevertheless, more than 200 homes were destroyed or severely damaged. Most bridges met a similar fate. Figure 12.17 Lahar at Empty Redoubt. In November 1985, lahars were produced during the eruption of Nevado del Ruiz, a 5,300-meter volcano in the Andes Mountains of Colombia. The eruption melted much of the snow and ice that capped the uppermost 600 meters of the peak, producing torrents of hot, viscous mud, ash, and debris. The lahars moved outward from the volcano, following the valleys of three rain-swollen rivers that radiate from the peak. The flow that moved down the valley of the Lagunillas River was the most destructive. It devastated the town of Armero, 48 kilometers from the mountain, causing more than 25,000 deaths. Earth flow. We have seen that debris flows are frequently confined to channels in semi-arid regions. In contrast, earth flows most often form on hillsides in humid areas during times of heavy precipitation or snowmelt. When water saturates the soil and regolith on a hillside, the material may break away, leaving a scar on the slope and forming a tongue or teardrop-shaped mass that flows downslope. This small tongue-shaped earth flow occurred on a newly formed slope along a recently constructed highway in central Illinois. It formed in clay-rich material following a period of heavy rain. Notice the small slump at the head of the earth flow. Figure 12.18 Earth flow. The materials most commonly involved are rich in clay and silt and contain only small proportions of sand and coarser particles. Earth flows range in size from bodies a few meters long, a few meters wide, and less than a meter deep to masses more than 1 kilometer long, several hundred meters wide, and more than 10 meters deep. Because earth flows are quite viscous, they generally move at slower rates than the more fluid debris flows described in the preceding section. They are characterized by a gradual movement that may go on for periods ranging from days to years. Depending on the steepness of the slope and the material's consistency, measured velocities range from less than a millimeter a day up to several meters a day. Over the time span that earth flows are active, movement is typically faster during wet periods than during drier times. In addition to occurring as isolated hillside phenomena, earth flows commonly take place in association with large slumps. In this situation, they may be seen as tongue-like flows at the base of the slump block. Concept checks 12.4. 1. Without looking at figures 12.12 and 12.13, sketch and label a simple cross-section of a slump. 2. Both slumps and rock slides move by sliding. How do these processes differ? 3. What factors led to the massive rock slide at Gros Ventre, Wyoming? 4. How is a lahar different from a debris flow that might occur in Southern California? 5. Contrast earth flows and debris flows. 12.5 Very slow mass movements. Review the general characteristics of slow mass movement processes and describe the unique issues associated with a permafrost environment. Movements such as rock slides, rock avalanches, and lahars are certainly the most spectacular and catastrophic forms of mass movement. These dangerous events deserve intensive study to enable more effective prediction, timely warnings, and better controls to save lives. However, because of their large size and spectacular nature, they give us a false impression of their importance as mass movement processes. Indeed, sudden movements are responsible for moving less material than the slower and far more subtle action of creep. Whereas rapid types of mass movement are characteristic of mountains and steep hillsides, creep takes place on both steep and gentle slopes and is thus much more widespread. Creep. Creep is a type of mass movement that involves the gradual downhill movement of soil and regolith. One factor that contributes to creep is the alternating expansion and contraction of surface material caused by freezing and thawing, or wetting and drying. As shown in Figure 12. 19. Freezing or wetting lifts particles at right angles to the slope, and thawing or drying allows the particles to fall back to a slightly lower level. Each cycle therefore moves the material a tiny distance downslope. Creep is aided by anything that disturbs the soil, such as raindrop impact and disturbance by plant roots and burrowing animals. Creep is also promoted when the ground becomes saturated with water. Following a heavy rain or snowmelt, a waterlogged soil may lose its internal cohesion, allowing gravity to pull the material downslope. Because creep is imperceptibly slow, the process cannot be observed in action. However, the effects of creep can be observed. Creep causes fences and utility poles to tilt and retaining walls to be displaced. The repeated expansion and contraction of the surface material causes a net downslope migration of soil and rock particles. Smart Figure 12.19 Creep. Smart Figure 12.19 Full Alternative Text Description. Solifluction. When soil is saturated with water, the soggy mass may flow downslope at a rate of a few millimeters or a few centimeters per day or per year. Such a process is called solifluction. It is a type of mass movement that is common wherever water cannot escape from the saturated surface layer by infiltrating to deeper levels. A dense clay hardpan in soil or an impermeable bedrock layer can promote solifluction. Watch tutorial, Creep. Solifluction is also common in regions underlain by permafrost. Permafrost refers to the permanently frozen ground that occurs in association with Earth's harsh tundra and subarctic climates. Solifluction occurs in a zone above the permafrost called the active layer, which thaws to a depth of about a meter during the brief high-latitude summer and then refreezes in winter. During the summer season, water is unable to percolate into the impervious permafrost layer below. As a result, the active layer becomes saturated and slowly flows. The process can occur on slopes as gentle as 2 to 3 degrees. Where there is a well-developed mat of vegetation, a solifluction sheet may move in a series of well-defined lobes or as a series of partially overriding folds. Solifluction occurs in permafrost regions when the active layer thaws in summer. Figure 12.20 Solifluction lobes near the Arctic Circle in Alaska. The sensitive permafrost landscape. Many of the mass movement disasters described in this chapter had sudden and disastrous impacts on people. When the activities of people cause ice contained in permanently frozen ground to melt, the impact is more gradual and less deadly. Nevertheless, because permafrost regions are sensitive and fragile landscapes, the scars resulting from poorly planned actions can remain for generations. Permanently frozen ground, known as permafrost, occurs where summers are too short and cool to melt more than a shallow surface layer. Deeper ground remains frozen year-round. Permafrost is extensive in the lands surrounding the Arctic Ocean. Strictly speaking, permafrost is defined only on the basis of temperature, that is, it is ground with temperatures that have remained below 0 degrees Celsius continuously for 2 years or more. The degree to which ice is present in the ground strongly affects the behavior of the surface material. Knowing how much ice is present and where it is located is very important when it comes to constructing roads, buildings, and other projects in areas underlain by permafrost. When people disturb the surface, such as by removing the insulating vegetation mat or by constructing roads and buildings, the delicate thermal balance is disturbed, and the permafrost can thaw. Thawing produces unstable ground that may slide, slump, subside, and undergo severe frost heaving. When a heated structure is built directly on permafrost that contains a high proportion of ice, thawing creates soggy material into which a building can sink. One solution is to place buildings and other structures on piles, like stilts. The piles allow sub-freezing air to circulate between the floor of the building and the soil and thereby keep the ground frozen. This building, located south of Fairbanks, Alaska, subsided because of thawing permafrost. Notice that the right side, which was heated, settled much more than the unheated porch on the left. Smart Figure 12.21 When permafrost thaws. Concept checks 12.5. 1. Describe the basic mechanisms that contribute to creep. How might you recognize that creep is occurring? 2. During what season does solifluction in the Arctic occur? Explain why it occurs only during that season. 3. What is permafrost? How might disturbing permafrost lead to unstable ground that may slide, flow, or subside? Watch tutorial, Permafrost. Concepts in review, mass movement. On slopes, the work of gravity. 12.1 The importance of mass movement. Describe how mass movement processes can cause natural disasters and discuss the role that mass movement plays in the development of landscapes. Key term. Mass movement. After weathering breaks apart rock, gravity moves the debris downslope, in a process called mass movement. Sometimes this occurs rapidly as a landslide, and at other times the movement is slower. Landslides are a significant geologic hazard, taking many lives and destroying property. Mass movement serves an important role in landscape development. It widens stream valleys and helps tear down the mountains thrust up by plate tectonics. Figure 12.7 to 1 full alternative text description. The Oso landslide shown in the chapter opening photo surprised many people. In this detailed topographic map of the valley, the deposit of the 2014 Oso landslide is shown by the crosshatch pattern. Colored areas show older landslide deposits, distinguished by age. Study the map and explain whether you think the 2014 event should have been anticipated. 12.2 Controls and Triggers of Mass Movement. Summarize the factors that control and trigger mass movement processes. Key terms. Trigger angle of repose. An event that initiates a mass movement process is referred to as a trigger. The addition of water, oversteepening of the slope, removal of vegetation, and shaking due to an earthquake are 4 important examples of triggers. Not all landslides are triggered by one of these 4 processes, but many are. Water added to a slope can expand the pores, separating grains and causing them to lose their cohesion. Water also lubricates the contacts between the grains and adds a significant amount of mass to a wetted slope. Granular materials can pile up to a certain angle of slope, but granular piles steeper than that critical angle will spontaneously collapse outward to form a gentler slope. For most geologic materials, this angle of repose varies between 25 and 40 degrees from horizontal. Oversteepened slopes are likely to fail with a landslide. The roots of plants act as a 3-dimensional net that holds soil and regolith particles in place. When the plants die, the soil loses an important support structure. Plants may be removed naturally or by humans seeking to harvest timber, plant crops, or build structures. Earthquakes are significant triggers that deliver an energetic jolt to slopes poised on the brink of failure. Do all mass movement events have triggers? Explain. 12.3 Classification of mass movement processes. List and explain the criteria that are commonly used to classify mass movement processes. Key terms. Fall talus slope slide. Flow. Rock avalanche. There are a variety of earth materials and a variety of rates of mass movement. The type of material and the nature of the motion are combined into classifying terms for the different types of mass movement. Rockfalls occur when pieces of bedrock detach and fall freely through the air, slamming into the ground below with tremendous force. Repeated rockfalls generate a talus slope, the characteristic apron, of angular rock debris that accumulates below mountain cliffs. Slides occur when discrete blocks of rock or unconsolidated material slip downslope on a planar or curved surface. Unlike in a fall, the material in a slide does not drop through the air. Flows occur when individual grains or particles move randomly in a slurry, a viscous mixture of water-saturated materials. Rock and debris avalanches on Earth and Mars move incredibly rapidly over surprising distances. Other forms of mass movement are much slower, moving perhaps only millimeters per year. 12.4 Common forms of mass movement, rapid to slow. Distinguish among rockfall, rockslide, debris avalanche, debris flow, slump, and earth flow. Key terms. Slump, rockslide, debris, avalanche, debris, flow, mudflow, lahar, earth flow. A slump is a distinctive and common form of mass movement in which coherent blocks of material move downhill on a spoon-shaped slip surface. Slumps are often marked by curved scarps that open up at their tops. They are frequently triggered by oversteepening, such as that caused by stream erosion of a valley wall. Rockslides are rapid mass movement events in which a coherent block of rock slides downhill along a planar surface. Often this is a pre-existing structure such as a joint or a bedding plane. Situations where these surfaces dip into a valley at an angle are especially dangerous, when the slide transforms into a chaotic debris avalanche. Debris flows occur when unconsolidated soil or regolith becomes saturated with water and moves downhill in a slurry, picking up other objects along the way. Varieties of debris flow include mudflows, which are dominated by small particle sizes, and lahars, which involve volcanic materials. Debris flows can move quickly, up to 30 kilometers per hour. Earth flow is characterized by a similar loss of coherence between grains in unconsolidated material, but it is much slower than a debris flow. Typically, sites of earth flow show an uphill scarp and a lobe of viscous soil on the downhill side. This rockslide occurred in the rugged Himalayas of northern India. Identify a feature in the photo that may have been a factor that contributed to the slide. Speculate about what might have triggered the event. 12.5 Very slow mass movements. Review the general characteristics of slow mass movement processes and describe the unique issues associated with a permafrost environment. Key terms. Creep solifluction permafrost. Creep is a widespread and important form of mass movement that is very slow. It occurs when freezing causes soil particles to be pushed out away from the slope, only to drop down to a lower position following thawing. In contrast, solifluction is the gradual flow of a saturated surface layer that is underlain by an impermeable zone. In Arctic regions, the impermeable zone is permafrost. Permafrost, permanently frozen ground, covers large portions of North America and Siberia. Constructing buildings and other infrastructure in such regions requires special planning. Leaking heat can melt permafrost, causing a loss of volume and triggering flow in the formerly frozen soil. The resulting subsidence can be devastating. This pipeline carries heated oil from Alaska's North Slope to a port along Alaska's south coast. Notice that the pipeline is not buried but rather suspended above ground. Suggest a reason the pipeline in this image is not buried. Give it some thought. 1. Describe a type of mass movement that might occur in your home area. Remember to consider characteristics such as climate, surface materials, and steepness of slopes. Does your example have a trigger? 2. Rivers, groundwater, glaciers, wind, and waves can all move and deposit sediment. Geologists refer to these phenomena as agents of erosion. Mass movement also involves the movement and deposition of sediment, yet it is not classified as an agent of erosion. How is mass movement different? 3. Describe at least one situation in which an internal process might cause or contribute to a mass movement event. 4. Do you think it is likely that landslides frequently occur on the moon? Explain why or why not. 5. Heavy rains in late July 2010 triggered the mass movement that occurred in this mountain valley near Durango, Colorado. Heavy equipment is clearing away material that blocked railroad tracks and significantly narrowed the adjacent stream channel. Was this event more likely a rockfall, creep, or a debris flow? Most of us are familiar with the phrase, one thing leads to another. It certainly applies to the Earth system. Suppose the material from the mass movement event shown here had completely filled the stream. What other natural hazard might have developed? 6. When the rail line in the accompanying photo was built in rural Alaska in the 1930s, the terrain was relatively level. Not long after the railroad was completed, a great deal of subsidence and shifting of the ground occurred, turning the tracks into the roller coaster shown here. As a result, the rail line had to be abandoned. Suggest a reason the ground became unstable and shifted. 7. This photo shows landslide debris atop Buckskin Glacier in Denali National Park in the rugged Alaska Range. The glacier feeds a river that flows into Cook Inlet, just west of the city of Anchorage. Cook Inlet is an arm of the North Pacific. Based on what you learned about sorting of sediment in Chapter 7, would you expect the material deposited by the landslide to be well sorted? Why or why not? Also referring to Chapter 7 and Figure 7.7, would you expect the particles in the landslide debris to be rounded or angular? Explain. These mountains are clearly being sculpted by glaciers. However, other processes also have important roles. Identify these processes and briefly describe the role that each plays in the evolution of this mountainous landscape. 8. Mass movement is influenced by many processes associated with all four spheres of the Earth system. Select 2 items from the list below. For each, outline a series of events that relate the item to various spheres and to a mass movement process. The following example does this for the term frost wedging. Frost wedging involves rock being broken when water freezes. Freeze-thaw cycles promote frost wedging. When frost wedging loosens a rock on a cliff, the fragment tumbles to the base of the cliff. This event, rockfall, is an example of mass movement. Now you give it a try. Use your imagination. Deforestation. Spring thaw melting snow. Highway road cut. Crashing waves. Cavern formation. 9. The Swift Creek landslide is a large, complex slump in northwest Washington state that transitions into an earth flow and also generates debris flows during heavy rain events. Explore the Swift Creek Landslide Observatory website. The landslide moves on average 3 to 4 meters per year. That's about 1 centimeter per day. To see this slow movement over an extended period, click time-lapse. To try out the video generator, using these settings, start date, 01/01/2007 end date, 01/01/2014 time of day, between 12 to 3 p.m. camera, upper. Frame rate, medium video length, 10 seconds. Then click generate. After you try this, use the video generator to determine whether the Swift Creek landslide moves more during the wet season or during the dry season. Mastering Geology trademark. Looking for additional review and test prep materials? Visit the study area in Mastering Geology to enhance your understanding of this chapter's content by accessing a variety of resources, including self-study quizzes, geoscience animations, smart figures, mobile field trips, Project Condor quadcopter videos, in the news RSS feeds, flashcards, web links, and an optional Pearson e-text. Chapter 13 Running Water. The Colorado River winding through Canyonlands National Park in southern Utah. When this meandering path was established, the river flowed across a relatively flat landscape. Subsequently, the region was gradually lifted upward, while downward erosion lowered the riverbed. The meandering pattern persists, but the loops, locked within confining walls, are now referred to as incised meanders. Focus on concepts. Each statement represents the primary learning objective for the corresponding major heading within the chapter. After you complete the chapter, you should be able to 13.1 List the hydrosphere's major reservoirs and describe the different paths that water takes through the hydrologic cycle. 13.2 Describe the nature of drainage basins and river systems. Sketch and briefly explain 4 basic drainage patterns. 13.3 Discuss streamflow and the factors that cause it to change. 13.4 Outline the ways in which streams erode, transport, and deposit sediment. 13.5 Contrast bedrock and alluvial stream channels. Distinguish between 2 types of alluvial channels. 13.6 Contrast narrow V-shaped valleys, broad valleys with floodplains, and valleys that display incised meanders or stream terraces. 13.7 List the major depositional landforms associated with streams and describe the formation of these features. 13.8 Summarize the various categories of floods and the common measures of flood control. Consider the bittersweet relationship we have with rivers. They are vital economic tools, used as highways to move goods and as sources of water for irrigation and energy, as well as prime locations for recreation. When considered as part of the Earth system, rivers and streams represent a fundamental link in the constant cycling of our planet's water. As streams move across the land, they erode more terrain and transport more sediment than any other process. Soils and other materials can be washed away, only to be deposited elsewhere. Because human populations concentrate along rivers, flooding represents enormous potential for destruction and loss of life. This chapter provides an overview of the hydrologic cycle, the nature of river systems, the types of river channels and the factors that produce them, the influences of running water on our planet's landscapes, and the nature of floods and their impact on people. 13.1 Earth as a system, the hydrologic cycle. List the hydrosphere's major reservoirs and describe the different paths that water takes through the hydrologic cycle. Water is constantly moving among Earth's different spheres, the hydrosphere, the atmosphere, the geosphere, and the biosphere. This unending circulation of water is called the hydrologic cycle. Earth is the only planet in the solar system that has a global ocean and a hydrologic cycle. Earth's water. Water is almost everywhere on Earth, in the oceans, glaciers, rivers, lakes, air, soil, and living tissue. All these reservoirs constitute Earth's hydrosphere. In all, the water content of the hydrosphere is an estimated 1.36 billion cubic kilometers. The vast bulk of it, about 96.5%, is stored in the global ocean. Ice sheets and glaciers account for an additional 1.76%, leaving just slightly more than 2% to be divided among lakes, streams, groundwater, and the atmosphere. Although the percentage of Earth's total water found in each of the latter sources is just a small fraction of the total inventory, the absolute quantities are great. Figure 13.1 Full alternative text description. Figure 13.1 Distribution of Earth's water. Water's paths. The hydrologic cycle is a gigantic, worldwide system powered by energy from the sun, in which the atmosphere provides a vital link between the oceans and continents. Evaporation, the process by which liquid water changes into water vapor, is how water enters the atmosphere from the ocean and, to a much lesser extent, from the continents. Winds transport this moisture-laden air, often great distances. Complex processes of cloud formation eventually result in precipitation. The precipitation that falls into the ocean has completed its cycle and is ready to begin another. The water that falls on the continents, however, must make its way back to the ocean. The primary movement of water through the cycle is shown by the large arrows. A number refers to the annual amount of water taking a particular path. Smart Figure 13.2 The hydrologic cycle. Smart Figure 13.2 Full alternative text description. What happens to precipitation once it has fallen on land? A portion of the water soaks into the ground, slowly moving downward, then moving laterally, and finally seeping into lakes, streams, or directly into the ocean. When the rate of rainfall exceeds the ground's ability to absorb it, the surplus water flows over the surface into lakes and streams, a process called runoff. Much of the water that infiltrates or runs off eventually returns to the atmosphere because of evaporation from the soil, lakes, and streams. Also, some of the water that soaks into the ground is absorbed by plants, which then release it into the atmosphere. This process is called transpiration. Because both evaporation and transpiration involve the transfer of water from the surface directly to the atmosphere, they are often considered together as the combined process of evapotranspiration. Watch tutorial, The Water Cycle. Storage in glaciers. When precipitation falls in very cold places, at high elevations or high latitudes, the water may not immediately soak in, run off, or evaporate. Instead, it may become part of a snowfield or a glacier. In this way, glaciers store large quantities of water on land. If present-day glaciers were to melt and release all their water, sea level would rise by several dozen meters. Such a rise would submerge many heavily populated coastal areas. As you will see in Chapter 15, over the past 2 million years, huge ice sheets have formed and melted on several occasions, each time affecting the balance of the hydrologic cycle. Water balance. Figure 13.2 also shows Earth's overall water balance, or the volume that passes through each part of the cycle annually. The amount of water vapor in the air at any one time is just a tiny fraction of Earth's total water supply. But the absolute quantities that are cycled through the atmosphere over a 1-year period are immense, some 380,000 cubic kilometers. Enough to cover Earth's entire surface to a depth of about 1 meter. It is important to know that the hydrologic cycle is balanced. Because the total amount of water vapor in the atmosphere remains about the same, the average annual precipitation worldwide must be equal to the quantity of water evaporated. However, for all the continents taken together, precipitation exceeds evaporation. Conversely, over the oceans, evaporation exceeds precipitation. Because the level of the world ocean is not dropping, the system must be in balance. In Figure 13. 2. The 36,000 cubic kilometers of water that annually makes its way from the land to the ocean causes enormous erosion. In fact, this immense volume of moving water is the single most important agent sculpting Earth's land surface. In the rest of this chapter, we will examine stream characteristics, erosion and deposition by running water, and floods, a significant natural hazard. Did you know? Each year a field of crops may transpire the equivalent of a water layer 2 feet deep over the entire field. The same area of trees may pump twice this amount into the atmosphere. Concept checks 13.1. 1. Describe or sketch the movement of water through the hydrologic cycle. Once precipitation has fallen on land, what paths might the water take? 2. What is meant by the term evapotranspiration? 3. Over the oceans, evaporation exceeds precipitation, yet sea level does not drop. Explain why. 13.2 Running water. Describe the nature of drainage basins and river systems. Sketch and briefly explain 4 basic drainage patterns. Much of the precipitation that falls on land either soaks into the ground or remains at the surface, moving downslope as runoff. The amount of water that runs off compared to the amount that infiltrates depends on several factors: the intensity and duration of rainfall, the amount of water already in the soil, the nature of the surface material, the slope of the land, and the extent and type of vegetation. When the surface material is impermeable or when it becomes saturated, runoff is the dominant process. Runoff is also high where slopes are steep and in cities where large areas are covered with impermeable buildings, roads, and parking lots. Runoff initially flows in broad, thin sheets across slopes in a process called sheet flow. This unconfined flow eventually develops threads of current that form tiny channels called rills. Rills meet to form gullies, which join to form streams. Then, when they reach an undefined size, they are called rivers. Although the terms river and stream are often used interchangeably, geologists define stream as water that flows in a channel, regardless of size. River, on the other hand, is a general term for streams that carry substantial amounts of water and have numerous tributaries. Drainage basins. Every stream drains an area of land called a drainage basin, or watershed. Each drainage basin is bounded by an imaginary line called a divide, something that is clearly visible as a sharp ridge in some mountainous areas but can be more difficult to determine when the topography is subdued. The outlet, where the stream exits the drainage basin, is at a lower elevation than the rest of the basin. A drainage basin or watershed is the area drained by a stream and its tributaries. Boundaries between basins are called divides. Figure 13.3 Drainage basin and divide. Drainage divides range in scale from a small ridge separating 2 gullies on a hillside to a continental divide that splits an entire continent into enormous watersheds. The Mississippi River has the largest drainage basin in North America, collecting and carrying 40% of the flow in the United States. The drainage basin of the Mississippi River forms a funnel that stretches from Montana and southern Canada in the west to New York State in the east that runs down to a spout in Louisiana. It consists of many smaller drainage basins. The drainage basin of the Yellowstone River is one of many that contribute water to the Missouri River, which, in turn, is one of many that make up the drainage basin of the Mississippi River. Smart Figure 13.4 Mississippi River Drainage Basin. Smart Figure 13.4 Full alternative text description. By looking at the drainage basin in Figure 13.3, it should be obvious that slopes cover most of the area. Water erosion on the hillsides is aided by the impact of raindrops and by sheet flow, moving downslope as sheets or in rills toward a stream channel. Hillslope erosion is the main source of fine particles carried in stream channels. Watch tutorial, Drainage basins. If you could observe streams in an area similar to that depicted in Figure 13.3 over several years, you would see many of them lengthen by headward erosion, that is, by extending the heads of their channels upslope. Headward erosion occurs when the surface flow converging at the head of a channel has enough power to cut the channel deeper. This lowering of the channel creates steeper headward slopes that erode more quickly. Thus, through headward erosion, a valley extends into previously undissected terrain. A stream lengthens its course by extending the head of its valley upslope into previously undissected terrain. Smart Figure 13.5 Headward erosion. River systems. A river system includes not only its network of stream channels but its entire drainage basin. It can be divided into 3 zones based on the process that dominates in each. These are the zones of sediment production, sediment transport, and sediment deposition. It is important to recognize that sediment is being eroded, transported, and deposited along the entire length of a stream, regardless of which process is dominant within each zone. Each of the 3 zones is based on the process that dominates in that part of the river system. Watch tutorial, Headward erosion. Figure 13.6 Zones of a river. Figure 13.6 Full alternative text description. Sediment production. The zone of sediment production, where most of the sediment is derived, is located in the headwaters region of the river system. Much of the sediment carried by streams begins as bedrock that is subsequently broken down by weathering, and then moved downslope by mass wasting and by way of sheet flow and rills. Bank erosion can also contribute significant amounts of sediment. In addition, scouring of the channel bed deepens the channel and adds to the stream's sediment load. Sediment transport. Downstream from the zone of sediment production, sediment acquired by a stream is transported through the channel network along sections referred to as trunk streams. When trunk streams are in balance, the amount of sediment eroded from their banks equals the amount deposited elsewhere in the channel. Although trunk streams rework their channels over time, they are not a source of sediment, nor do they accumulate or store it. Sediment deposition. When a river approaches the ocean or another large body of water, it slows, and the energy to transport sediment is greatly reduced. Most of the sediments either accumulate at the mouth of the river to form a delta, are reconfigured by wave action to form a variety of coastal features, or are moved far offshore by ocean currents. Because coarse sediments tend to be deposited upstream, it is primarily the fine sediments that eventually reach the ocean. Taken together, erosion, transportation, and deposition are the processes by which rivers move Earth's surface materials and sculpt landscapes. Did you know? North America's largest river is the Mississippi. South of Cairo, Illinois, where the Ohio River joins it, the Mississippi is more than 1 mile wide. Each year the mighty Mississippi carries about 500 million tons of sediment to the Gulf of Mexico. Drainage patterns. Drainage systems, which are interconnected networks of streams, can exhibit a variety of patterns. The pattern that develops depends primarily on the kind of rock present and/or the structural pattern of joints, faults, and folds. Figure 13.7 illustrates 4 drainage patterns. Networks of streams form a variety of patterns. The mobile field trip shows how water gaps form, such as those in Part D of this figure. Smart Figure 13.7 Drainage patterns. Smart Figure 13.7 Full alternative text description. Dendritic pattern. The most common drainage pattern is the dendritic pattern, so called because it resembles the branching pattern of a deciduous tree. A dendritic pattern forms where the underlying material is relatively uniform in its resistance to erosion, and hence does not control the pattern of stream flow. The pattern is therefore determined chiefly by the direction of slope of the land. Watch mobile field trip, the water gap at Sheep Mountain. Radial pattern. When streams diverge from a central area like spokes from the hub of a wheel, the pattern is said to be radial. This pattern typically develops on isolated volcanic cones and domal uplifts. Rectangular pattern. A rectangular pattern exhibits many right-angle bends. This pattern develops when the bedrock is crisscrossed by a series of joints and/or faults. Because fractured rock tends to weather and erode more easily than unbroken rock, the geometric pattern of joints guides the paths of streams as they carve their valleys. Trellis pattern. A trellis pattern is a rectangular drainage pattern in which tributary streams are nearly parallel to one another, and have the appearance of a garden trellis. This pattern forms in areas underlain by alternating bands of resistant and less resistant rock, and is particularly well displayed in the folded Appalachian Mountains, where both weak and strong strata outcrop in nearly parallel belts. Water gaps occur where a stream cuts across ridges of resistant rock. Formation of a water gap. To fully understand the drainage pattern displayed by a stream, it is often useful to consider a stream's entire history. For example, river valleys occasionally cut through a ridge or mountainous topography that lies across their path. This situation is illustrated by the trellis pattern in Figure 13.7d. The steep-walled notch followed by the river is called a water gap. Why do streams cut across such structures and not flow around them? One possibility is that a superposed stream eroded its channel into an existing structure. This can occur when folded beds or resistant rocks are buried beneath layers of relatively flat-lying sediments, or sedimentary strata. Streams originating on the overlying strata establish their courses without regard to the structures below. Then, as the valley deepens, the river continues to cut its valley into the underlying structure. Concept checks 13.2. 1. List several factors that cause infiltration and runoff to vary from place to place and time to time. 2. Draw a simple sketch of a drainage basin and a divide and label each. 3. What are the three main zones of a river system? 4. Prepare a simple sketch of the four drainage patterns discussed in this section. Briefly describe why streams exhibit each pattern. 13.3 Streamflow characteristics. Discuss streamflow and the factors that cause it to change. The water in stream and river channels moves under the influence of gravity. In very slowly flowing streams, water moves in nearly straight-line paths parallel to the stream channel. This is called laminar flow. However, streams typically exhibit turbulent flow. Strong turbulent behavior occurs in whirlpools and eddies, as well as in roiling whitewater rapids. Even streams that appear smooth on the surface often exhibit turbulent flow near the bottom and sides of the channel, where flow resistance is greatest. Turbulence contributes to a stream's ability to erode its channel because it acts to lift sediment from the streambed. Most often streamflow is turbulent. Figure 13.8 Laminar and turbulent flow. Figure 13.8 Full alternative text description. An important factor influencing stream turbulence is the water's flow velocity. As the velocity of a stream increases, the flow becomes more turbulent. Flow velocities can vary significantly from place to place along a stream channel, as well as over time, in response to variations in the amount and intensity of precipitation. If you have ever waded into a stream, you may have noticed that the strength of the current increased as you moved into deeper parts of the channel. This is related to the fact that frictional resistance is greatest near the banks and bed of a stream channel. Flow velocities are determined at gauging stations by averaging measurements taken at various locations across the stream's channel. Some sluggish streams have flow velocities of less than 1 km per hour, whereas stretches of some fast-flowing rivers may exceed 30 km per hour. Factors affecting flow velocity. The ability of a stream to erode and transport material is directly related to its flow velocity. Even slight variations in flow rate can lead to significant changes in the sediment load transported by a stream. Factors that influence flow velocities and, therefore, control a stream's potential to do a work include channel slope, or gradient, channel cross-sectional shape, channel size and roughness, and discharge, or the amount of water flowing in the channel. Gradient. The slope of a stream channel, expressed as the vertical drop of a stream over a specified distance, is called gradient. Portions of the lower Mississippi River have very low gradients, about 10 centimeters or less per kilometer. By contrast, some mountain streams have channels that drop at a rate of more than 40 meters per kilometer, a gradient 400 times steeper than that of the lower Mississippi. Gradient also varies along the length of a particular channel. When the gradient is steeper, more gravitational energy is available to drive channel flow. Channel shape. As water in a stream channel moves, it encounters a significant amount of frictional resistance. The cross-sectional shape determines, to a large extent, the amount of flow in contact with the banks and bed of the channel. This measure is referred to as the wetted perimeter. The most efficient channel is one with the least wetted perimeter for its cross-sectional area. Figure 13.9 compares two channels that differ only in shape. One is wide and shallow, the other is narrow and deep. Although the cross-sectional areas of the two are identical, the narrow and deep one has less water in contact with the channel and therefore less frictional drag. As a result, if all other factors are equal, the water will flow more efficiently and at a higher velocity in a channel that is roughly as wide as it is deep than in one that is wide and shallow. The stream with the smaller wetted perimeter has less frictional drag and will flow more rapidly, all else being equal. Figure 13.9 Influence of channel shape on velocity. Figure 13.9 Full alternative text description. Channel size and roughness. All other factors being equal, flow velocities are higher in large channels than in small channels. The depth of the water in a given channel also affects the frictional resistance that the channel exerts on flow. Maximum flow velocity occurs when a stream is bank full, before water starts to inundate the floodplain. At this stage, the channel's ratio of the cross-sectional area to wetted perimeter is highest, and streamflow is most efficient. A final factor is how rough a channel is. Elements such as boulders, irregularities in the channel bed, and woody debris create turbulence that significantly reduces flow velocity. Did you know? The Amazon River is responsible for about 20% of all the water reaching the ocean via rivers. Its nearest rival, Africa's Congo River, delivers about 4% of the total. Discharge. Streams vary in size from small headwater creeks less than a meter wide to large rivers with widths of several kilometers. The size of a stream channel is largely determined by the amount of water supplied from the drainage basin. The measure most often used to compare the size of streams is discharge, the volume of water flowing past a certain point in a given unit of time. Discharge, usually measured in cubic meters per second or cubic feet per second, is determined by multiplying a stream's cross-sectional area by its velocity. The largest river in North America, the Mississippi, has an average discharge at its mouth of about 16,800 cubic meters per second. That figure is dwarfed by South America's mighty Amazon River, which discharges 13 times more water than the Mississippi. Smart Figure 13.10 The mighty Mississippi near Helena, Arkansas. The Mississippi is North America's largest river. From head to mouth, it is nearly 3,900 kilometers long. Its watershed encompasses about 40% of the lower 48 states and includes all or parts of 31 states and 2 Canadian provinces. Average discharge at its mouth is about 16,800 cubic meters per second. Watch Mobile Field Trip, the Mississippi River. The discharge of a river system changes over time because of variations in the amount of precipitation received by the watershed. Studies show that when discharge increases, the width, depth, and flow velocity of the channel all increase predictably. As we saw earlier, when the size of the channel increases, proportionally less water is in contact with the bed and banks of the channel. Thus, friction, which acts to retard the flow, is reduced, resulting in an increase in the rate of flow. Monitoring stream flow. The U.S. Geological Survey maintains a network of about 7,500 stream gauging stations that collect basic data about the country's surface water resources. Data collected include flow velocity, discharge, and river stage. Stage is the height of the water surface relative to a fixed reference point. This measurement is frequently reported by the media, especially when a river approaches or surpasses flood stage. Streamflow measurements are essential components of river models used to make flood forecasts and issue warnings. There are other applications as well. The data are used in making decisions related to water supply allocations, operation of wastewater treatment plants, design of highway bridges, and recreation activities. Figure 13.11 Stream gauging stations. The United States has a dense network of stream gauging stations. To determine a channel's discharge, it is necessary to survey the channel to determine its shape and calculate its area. A stilling well measures the stage, and a current meter determines flow velocity. Figure 13.11 Full alternative text description. Changes downstream. One useful way of studying a stream is to examine its longitudinal profile. Such a profile is simply a cross-sectional view of a stream from its source area to its mouth, the point downstream where it empties into another water body, a river, a lake, or the ocean. Figure 13.12 shows that the most obvious feature of a typical longitudinal profile is its concave shape, a result of the decrease in slope that occurs from the headwaters to the mouth. In addition, local irregularities exist in the profiles of most streams. The flatter sections may be associated with lakes or reservoirs, and the steeper sections are sites of rapids or waterfalls. California's Kings River originates high in the Sierra Nevada and flows into the San Joaquin Valley. Figure 13.12 Full alternative text description. Figure 13.12 Longitudinal profile. The change in slope observed on most stream profiles is usually accompanied by an increase in discharge and channel size, and a reduction in sediment particle size. For example, data from successive gauging stations along most rivers show that, in humid regions, discharge increases toward the mouth. This occurs because, as we move downstream, more and more tributaries contribute water to the main channel. In the case of the Amazon, for example, about 1,000 tributaries join the main river along its 6,500-kilometer course across South America. Although the gradient decreases toward the mouth of a stream, increases in discharge and channel size and decreases in roughness more than offset the decrease in slope. Consequently, flow velocity usually increases toward the mouth. Smart Figure 13.13 Full alternative text description. Smart Figure 13.13 Channel changes from head to mouth. In order to accommodate the growing volume of water, channel size typically increases downstream as well. Recall that flow velocities are higher in large channels than in small channels. Furthermore, observations show a general decline in sediment size downstream, making the channel smoother and more efficient. Although the channel slope decreases, the gradient becomes less steep. Toward a stream's mouth, the flow velocity generally increases. This fact contradicts our intuitive assumption that narrow headwater streams are swift, whereas a broad river flowing across subtle topography will be slow. Actually, the increase in channel size and discharge and decrease in channel roughness that occur downstream compensate for the decrease in slope, making the stream more efficient. Thus, the average flow velocity is typically lower in headwater streams than in wide, placid-appearing rivers. Concept checks 13.3. Watch tutorial, head to mouth. 1. Contrast laminar flow and turbulent flow. 2. Summarize the factors that influence flow velocity. 3. What is a longitudinal profile? 4. What typically happens to channel width, channel depth, flow velocity, and discharge between the headwaters and the mouth of a stream? Briefly explain why these changes occur. 13. For the work of running water. Outline the ways in which streams erode, transport, and deposit sediment. Streams are Earth's most important erosional agents. Not only do they have the ability to downcut and widen their channels, but streams also have the capacity to transport enormous quantities of sediment delivered to them by overland flow, mass wasting, and groundwater. Eventually, much of this material is deposited to create a variety of landforms. Stream erosion. A stream's ability to accumulate and transport soil and weathered rock is aided by the work of raindrops, which knock sediment particles loose. When the ground is saturated, rainwater cannot infiltrate, so it flows downslope, transporting some of the material it dislodges. On barren slopes, the flow of muddy water often produces small channels, which in time can evolve into larger gullies. Once flow is confined in a channel, the erosional power of a stream is related to its slope and discharge. The rate of erosion is also dependent on the relative resistance of the bank and bed material. In general, channels composed of unconsolidated materials are more easily eroded than channels cut into bedrock. When a channel is sandy, the particles are easily dislodged from the bed and banks, and they are lifted into the moving water. Moreover, banks consisting of sandy material are often undercut, dumping even more loose debris into the water to be carried downstream. Banks that consist of coarse gravels or cohesive clay and silt particles tend to be relatively resistant to erosion. Thus, channels with cohesive silty banks are generally narrower than comparable ones with sandy banks. Streams cut channels into bedrock through three main processes: quarrying, abrasion, and corrosion. Quarrying. Quarrying involves the removal of blocks from the bed of a stream channel. This process is aided by fracturing and weathering that loosen the blocks sufficiently so they are movable during times of high flow rates. Quarrying is mainly a result of the impact forces exerted by flowing water. Abrasion. The process by which the bed and banks of a bedrock channel are ceaselessly bombarded by particles carried into the flow is termed abrasion. The individual sediment grains are also abraded by their many impacts with the channel and with one another. Thus, by scraping, rubbing, and bumping, abrasion erodes a bedrock channel and simultaneously smooths and rounds the abrading particles. That is why smooth, rounded cobbles and pebbles are found in streams. Abrasion also results in a reduction in the size of the sediments transported by streams. Features common to some bedrock channels are circular depressions known as potholes, which are created by the abrasive action of particles swirling in fast-moving eddies. The rotational motion of sand and pebbles acts like a drill that bores the holes. As the particles wear down to nothing, they are replaced by new ones that continue to drill the stream bed. Eventually, smooth depressions several meters across and deep may result. The rotational motion of swirling pebbles acts like a drill to create potholes. Figure 13.14 Potholes. Corrosion. Bedrock channels formed in soluble rock such as limestone are susceptible to corrosion, a process in which rock is gradually dissolved by the flowing water. Corrosion is a type of chemical weathering between the solutions in the water and the mineral matter that makes up the bedrock. Transport of sediment by streams. All streams, regardless of size, transport some weathered rock material. Streams also sort the solid sediment they transport because finer, lighter material is carried more readily than larger, heavier particles. Streams transport their load of sediment in three ways: in solution, in suspension, and by sliding, skipping, or rolling along the bottom. Streams transport their load of sediment in three ways. The dissolved and suspended loads are carried in the general flow. The bed load includes coarse sand, gravel, and boulders that move by rolling, sliding, and saltation. Smart Figure 13.15 Transport of sediment. Watch animation, sediment transport by streams. Dissolved load. Most of the dissolved load is brought to a stream by groundwater and is dispersed throughout the flow. When water percolates through the ground, it acquires soluble soil compounds. Then it seeps through cracks and pores in bedrock, dissolving additional mineral matter. Eventually, much of this mineral-rich water finds its way into streams. The velocity of streamflow has essentially no effect on a stream's ability to carry its dissolved load. Material in the solution goes wherever the stream goes. Precipitation of the dissolved mineral matter occurs when the chemistry of the water changes, when organisms extract mineral matter to create hard parts, or when the water enters an inland sea, located in an arid climate where the rate of evaporation is high. Suspended load. Usually streams transport the greatest amount of sediment as the suspended load. Indeed, the muddy appearance created by suspended sediment is the most obvious portion of a stream's load. Usually only very fine sand, silt, and clay particles are carried this way, but during flood stage, larger particles can also be transported in suspension. During flood stage, the total quantity of material carried in suspension also increases dramatically. People whose homes have become sites for the deposition of this material can verify this. An aerial view of the Colorado River in the Grand Canyon. Heavy rains washed sediment into the river. Figure 13.16 Suspended load. The type and amount of material carried in suspension are controlled by two factors: the flow velocity and the settling velocity of each sediment grain. Settling velocity is defined as the speed at which a particle falls through a still fluid. The larger the particle, the more rapidly it settles toward the streambed. In addition to size, the shape and specific gravity of particles also influence settling velocity. Flat grains sink through water more slowly than spherical grains, and dense particles fall toward the bottom more rapidly than less dense particles. As long as flow velocity exceeds settling velocity, sediment remains suspended and is transported downstream. Deposition occurs when flow velocity falls below the settling velocity of a particle. The speed at which a particle falls through still water is its settling velocity. Deposition of suspended particles occurs when their settling velocities are greater than the stream's flow velocity. Figure 13.17 Full alternative text description. Figure 13.17 Settling velocity. Bed load. Coarse materials, including coarse sands, gravels, and even boulders, typically move along the bed of a channel as bed load. The particles that make up the bed load move by rolling, sliding, and saltation. Sediment moving by saltation appears to jump or skip along the stream bed. This occurs as particles are propelled upward by collisions or lifted by the current and then carried downstream a short distance, until gravity pulls them back to the bed of the stream. Particles that are too large or heavy to move by saltation either roll or slide along the bottom, depending on their shape. The movement of bed load through a stream network tends to be less rapid and more localized than the movement of suspended load. A study conducted on a glacially fed river in Norway determined that suspended sediments took only a day to exit the drainage basin, while the bed load required several decades to travel the same distance. Depending on the discharge and slope of the channel, coarse gravels may only be moved during times of high flow, while boulders move only during exceptional floods. Once set in motion, large particles are usually carried short distances. Along some stretches of a stream, bed load cannot be carried at all until it is broken into smaller particles. Capacity and competence. A stream's ability to carry solid particles is described using two criteria, capacity and competence. Capacity is the maximum load of solid particles a stream can transport per unit time. The greater the discharge, the greater the stream's capacity for hauling sediment. Consequently, large rivers with high flow velocities have large capacities. Competence is a measure of a stream's ability to transport particles based on size rather than quantity. Flow velocity is key. Swift streams have greater competencies than slow streams, regardless of channel size. A stream's competence increases proportionately to the square of its velocity. Thus, if the velocity of a stream doubles, the impact force of the water increases 4 times, if the velocity triples, the force increases 9 times, and so forth. Hence, large boulders that are often visible in low water and seem immovable can, in fact, be transported during exceptional floods because of the stream's increased competence. By now it should be clear why the greatest erosion and transportation of sediment occurred during periods of high water, associated with floods. The increase in discharge results in greater capacity, the increased velocity produces greater competency. Rising velocity makes the water more turbulent, and larger particles are set in motion. In the course of a few days, or perhaps a few hours, a stream at flood stage can erode and transport more sediment than it does during several months of normal flow. Did you know? It is estimated that each year the world's rivers transport about 2.4 miles of weathered material to lakes and oceans, either as detrital sediment or as dissolved ions. If erosion occurred evenly over Earth's land surface, this quantity of sediment would represent a lowering of nearly 0.3 in over a 100-year span. Deposition of sediment by streams. Deposition occurs whenever a stream slows, causing a reduction in competence. Put another way, particles are deposited when the flow velocity is less than the settling velocity. As a stream's flow velocity decreases, sediment begins to settle, largest particles first. In this manner, stream transport provides a mechanism by which solid particles of various sizes are separated. This process, called sorting, explains why particles of similar size are deposited together. The general term for sediment deposited by streams is alluvium. Many different depositional features are composed of alluvium. Some occur within stream channels, some occur on the valley floor adjacent to a channel, and some are found at the mouth of a stream. We will consider the nature of these features later in the chapter. Concept checks 13.4. 1. Describe two processes by which streams cut channels in bedrock. 2. In what three ways does a stream transport its load? Which part of the load moves most slowly? 3. Explain the difference between capacity and competency. 4. What is settling velocity? What factors influence settling velocity? Does settling velocity affect the dissolved load? 13.5 Stream channels. Contrast bedrock and alluvial stream channels. Distinguish between two types of alluvial channels. A basic characteristic that distinguishes streamflow from overland flow is that it is confined in a channel. A stream channel can be thought of as an open conduit consisting of the streambed and banks that act to confine flow except, of course, during floods. Although this is somewhat oversimplified, we can divide stream channels into two basic types. Bedrock channels are channels in which the streams are actively cutting into solid rock. In contrast, when the bed and banks are composed mainly of unconsolidated sediment or alluvium, the channel is called an alluvial channel. Bedrock channels. As the name suggests, bedrock channels are cut into the underlying strata and typically form in the headwaters of river systems, where streams have steep gradients. The energetic flow tends to transport coarse particles that actively abrade the bedrock channel. Potholes are often visible evidence of the erosional forces at work. Steep bedrock channels often develop a sequence of steps and pools, relatively flat segments where alluvium tends to accumulate, and steep segments where bedrock is exposed. The steep areas contain rapids or, occasionally, waterfalls. Did you know? In 2014, renewable energy represented about 10% of U.S. energy consumption. Hydroelectric power plants contribute 26% of the country's renewable energy. Most of this energy is produced at large dams. The channel pattern exhibited by streams cutting into bedrock is controlled by the underlying geologic structure. Even when flowing over rather uniform bedrock, streams tend to exhibit winding or irregular patterns rather than flowing in straight channels. Anyone who has gone whitewater rafting has observed the steep, winding nature of a stream flowing in a bedrock channel. Alluvial channels. Alluvial channels form in sediment that was previously deposited in the valley. When the valley floor reaches sufficient width, material deposited by the stream can form a floodplain that borders the channel. Because the banks and beds of alluvial channels are composed of unconsolidated sediment, they can undergo significant changes in shape as material is continually being eroded, transported, and redeposited. The major factors affecting the shapes of these channels are the average size of the sediment being transported, the channel's gradient, and discharge. Alluvial channel patterns reflect a stream's ability to transport its load at a uniform rate while expending the least amount of energy. Thus, the size and type of sediment being carried help determine the nature of the stream channel. Two common types of alluvial channels are meandering channels and braided channels. Meandering channels. Streams that transport much of their load in suspension generally move in sweeping bends called meanders. These streams flow in relatively deep, smooth channels and primarily transport mud, sand, and occasionally fine gravel. The lower Mississippi River exhibits this type of channel. Meandering channels evolve over time as individual bends migrate across the floodplain. Most of the erosion is focused at the outside of the meander, where velocity and turbulence are greatest. In time, the outside bank is undermined, especially during periods of high water. Because the outside of a meander is a zone of active erosion, it is referred to as a cut bank. Debris acquired by the stream at the cut bank moves downstream, where the coarser material is generally deposited as point bars on the insides of meanders. In this manner, meanders migrate laterally by eroding the outside of the bends and depositing sediment on the inside, without appreciably changing their shape. By eroding its outer bank and depositing material on the inside of the bend, a stream is able to shift its channel. Smart Figure 13.18 Formation of cut banks and point bars. Smart Figure 13.18 Full alternative text description. Watch tutorial, Meandering rivers. In addition to migrating laterally, the bends in a channel also migrate down the valley. This occurs because erosion is more effective on the downstream side of the meander. Sometimes the downstream migration of a meander is slowed when it reaches a more resistant bank material. This allows the next meander upstream to gradually erode the material between the two meanders, as shown in Figure 13.19. Eventually, the river may erode through the narrow neck of land, forming a new, shorter channel segment called a cutoff. Because of its shape, the abandoned bend is called an oxbow lake. Oxbow lakes occupy abandoned meanders. Aerial view of an oxbow lake created by the meandering Green River near Bronx, Wyoming. Smart Figure 13.19 Formation of an oxbow lake. Did you know? In 2014, about 29% of the total U.S. hydroelectric power was generated in the state of Washington, which also has the nation's largest hydroelectric facility, Grand Coulee Dam on the Columbia River. Braided channels. Some streams consist of a complex network of converging and diverging channels that thread their way among numerous islands, or gravel bars. Because these channels have an interwoven appearance, they are called braided channels. Braided channels form where a large portion of a stream's load consists of coarse sediment and the stream has a highly variable discharge. Because the bank material is readily erodible, braided channels are wide and shallow. Watch animation, formation of an oxbow lake. The Knik River is a classic braided stream with multiple channels separated by migrating gravel bars. The Knik is choked with sediment from 4 melting glaciers in the Chugach Mountains north of Anchorage, Alaska. One setting in which braided streams form is at the end of glaciers, where there is a large seasonal variation in discharge. During the summer, large amounts of ice-eroded sediment are dumped into the meltwater streams flowing away from the glacier. However, when flow is sluggish, the stream deposits the coarsest material as elongated structures called bars. This process causes the flow to split into several paths around the bars. During the next period of high flow, the laterally shifting channels erode and redeposit much of this coarse sediment, thereby transforming the entire stream bed. In some braided streams, the bars have built semi-permanent islands anchored by vegetation. Figure 13.20 Braided stream. Concept checks 13.5. 1. Are bedrock channels more likely to be found near the head or the mouth of a stream? 2. Describe or sketch the evolution of a meander, including how an oxbow lake forms. 3. Describe a situation that might cause a stream channel to become braided. 13.6 Shaping stream valleys. Contrast narrow V-shaped valleys, broad valleys with floodplains, and valleys that display incised meanders or stream terraces. A stream valley consists of a channel and the surrounding terrain that directs water to the stream. It includes the valley floor, which is the lower, flatter area that is partially or totally occupied by the stream channel, and the sloping valley walls that rise above the valley floor on both sides. Alluvial channels often flow in valleys that have wide valley floors consisting of sand and gravel deposited in the channel and clay, and silt deposited by floods. Bedrock channels, on the other hand, tend to be located in narrow-shaped valleys. In some arid regions, where weathering is slow and rock is particularly resistant, narrow valleys having nearly vertical walls are also found. Such features are called slot canyons. Stream valleys exist on a continuum from narrow, steep-sided valleys to valleys that are so flat and wide that the valley walls are not discernible. This is a classic slot canyon in Utah's Capitol Reef National Park. Streams, with the aid of weathering and mass wasting, shape the landscape through which they flow. As a result, streams continuously modify the valleys they occupy. Base level and graded streams. Figure 13.21 Halls Creek Narrows. In 1875, John Wesley Powell, the pioneering geologist who led the first expedition down the Colorado River and through the Grand Canyon in 1869, and later headed the U.S. Geological Survey, introduced the concept of a downward limit to stream erosion, which he called base level. A fundamental concept in the study of stream activity, base level is defined as the lowest elevation to which a stream can erode its channel. Essentially, it is the level at which the mouth of a stream enters the ocean, a lake, or a trunk stream. Powell identified two types of base level. We may consider the level of the sea to be a grand base level, below which the dry lands cannot be eroded, but we may also have, for local and temporary purposes, other base levels of erosion. Exploration of the Colorado River of the West, page 203. Sea level, which Powell called grand base level, is now referred to as ultimate base level. Local base levels include lakes, resistant layers of rock, and rivers that act as base levels for their tributaries. All of these base levels limit a stream's ability to downcut its channel. Changes in base level cause corresponding adjustments in the work that streams perform. When a dam is built across a stream, the reservoir that forms behind it raises the base level of the stream. Upstream from the reservoir, the stream gradient is reduced, lowering its velocity and, hence, its sediment transporting ability. As a result, the stream deposits material, thereby building up its channel. This process continues until the stream again has a gradient sufficient to carry its load. The profile of the new channel will be similar to the old but somewhat higher. The base level upstream from the reservoir is raised, which reduces the stream's flow velocity and leads to deposition and a reduced gradient. Figure 13.22 Full alternative text description. If, on the other hand, base level is lowered by a drop in sea level, the stream will have excess energy and downcut its channel to establish a balance with its new base level. Erosion first occurs near the mouth and then progresses upstream, creating a new stream profile. Observing streams that adjust their profiles to changes in base level led to the concept of a graded stream. A graded stream has the necessary slope and other channel characteristics to maintain the minimum velocity required to transport the materials supplied to it. On average, a graded system is neither eroding nor depositing material but simply transporting it. When a stream reaches equilibrium, it becomes a self-regulating system in which a change in one characteristic causes a change in the others to counteract the effect. Figure 13.22 Building a dam. Did you know? The world's highest uninterrupted waterfall is Venezuela's Angel Falls. Named for American aviator Jimmy Angel, who first sighted the falls from the air in 1933, the water plunges 3,212 feet. Valley deepening. When a stream's gradient is steep, the channel is well above base level, and the dominant erosional process is downcutting, the lowering of the streambed toward base level. Abrasion caused by the bed load sliding and rolling along the bottom, as well as the hydraulic power of fast-moving water, slowly lowers the streambed. The result is usually a V-shaped valley with steep sides. A classic example of a V-shaped valley is the section of the Yellowstone River shown in Figure 13.23. The V-shaped valley, rapids, and waterfalls indicate that the river is downcutting vigorously. Figure 13.23 Yellowstone River. The most prominent features of V-shaped valleys are rapids and waterfalls. Both occur where the stream's gradient increases significantly, a situation usually caused by variations in the erodibility of the bedrock into which a stream channel is cutting. Resistant beds create rapids by acting as a temporary base level upstream while allowing downcutting to continue downstream. Over time, erosion usually eliminates the resistant rock. Waterfalls occur where streams make vertical drops. Valley widening. As a stream approaches a graded condition, in which it primarily works to transport sediment, downcutting becomes less dominant. At this point, the stream's channel takes on a meandering pattern, and more of its energy is directed from side to side. As a result, the valley widens as the river cuts away at one bank and then the other. The continuous lateral erosion caused by shifting meanders gradually produces a broad, flat valley floor covered with alluvium. This feature is called a floodplain because it becomes inundated when the river overflows its banks during flood stage. Over time, the floodplain will widen to a point where the stream is actively eroding the valley walls in only a few places. In the case of the lower Mississippi River, for example, the distance from one valley wall to the opposite wall sometimes exceeds 160 kilometers. Continuous side-to-side erosion by shifting meanders gradually produces a broad, flat valley floor. Alluvium deposited during floods covers the valley floor. Smart Figure 13.24 Development of an erosional floodplain. When a river erodes laterally and creates a floodplain as described, it is called an erosional floodplain. Floodplains can be depositional as well. Depositional floodplains are produced by major fluctuations in conditions, such as changes in baselevel or climate. The floodplain in California's Yosemite Valley is one such feature. It was produced when a glacier gouged the valley floor about 300 meters deeper than its former level. After the glacial ice melted, running water refilled the valley with alluvium. The Merced River currently winds across a relatively flat floodplain that forms much of the floor of Yosemite Valley. Watch Condor video, Meandering Rivers. Incised meanders and stream terraces. We usually find streams with highly meandering courses on floodplains in wide valleys. However, some rivers have meandering channels that flow in steep, narrow bedrock valleys. Such meanders are called incised meanders. A classic example is pictured in the chapter opening photo. How do these features form? Originally, the meanders probably developed on the floodplain of a stream that was in balance with its base level. Then, a change in base level caused the stream to begin downcutting. Such a change can be caused either by a drop in a downstream base level or by uplift of the land on which the river is flowing. For example, regional uplifting of the Colorado Plateau in the southwestern United States generated incised meanders on several rivers. As the plateau gradually rose, meandering rivers began downcutting because of their steepening gradient. These diagrams illustrate the development of incised meanders such as those shown in the chapter opening photo. Smart Figure 13.25 Incised meanders. Other features associated with a relative drop in base level are stream terraces. After a river that had been flowing on a floodplain has adjusted to a relative drop in base level, it may once again produce a floodplain at a level below the old one. As shown in Figure 13.26, remnants of the former floodplain are left as relatively flat surfaces above the newly forming floodplain. Terraces result when a stream adjusts to a relative drop in base level. Watch tutorial, Incised meanders. Smart Figure 13.26 Stream terraces. Smart Figure 13.26 Full alternative text description. Concept checks 13.6. Watch Condor video, River terraces and base level. 1. Define base level and distinguish between ultimate base level and local, or temporary, base level. 2. What is a graded stream? 3. Explain why V-shaped valleys often contain rapids and/or waterfalls. 4. Describe or sketch how an erosional floodplain develops. 5. Describe 2 situations that would trigger the formation of incised meanders. 13.7 Depositional landforms. List the major depositional landforms associated with streams and describe the formation of these features. Recall that streams continually pick up sediment in one part of their channel and deposit it downstream. These small-scale channel deposits are called bars. Such features, however, are only temporary, as the material will be picked up again and eventually carried to the ocean. In addition to sand and gravel bars, streams also create depositional features that have longer lifespans. These include deltas, natural levees, and alluvial fans. Deltas. Deltas form where sediment-laden streams enter the relatively still waters of a lake, an inland sea, or the ocean. As the stream's forward motion is slowed, sediments are deposited by the dying current, producing 3 types of beds. Foreset beds are composed of coarse particles that drop almost immediately upon entering the water to form layers that slope down current from the delta front. The foreset beds are subsequently covered by thin, horizontal topset beds deposited during floods. The finer silts and clays settle away from the mouth in nearly horizontal layers called bottomset beds. Structure and growth of a simple delta that forms in relatively quiet waters. Figure 13.27 Full alternative text description. Figure 13.27 Formation of a simple delta. As a delta grows outward from the shoreline, stream flow becomes sluggish because the gradient is decreasing. This eventually causes the channel to become choked with sediment. As a consequence, the river seeks shorter, higher gradient routes to base level. Figure 13.27 shows the main channel dividing into several smaller ones, called distributaries, that carry water away from the main channel in varying paths to base level. After numerous shifts in the main flow from one distributary to the next, a delta may grow into the triangular shape of the Greek letter delta, although several other shapes exist. Differences in the configurations of shorelines and variations in the nature and strength of wave activity are responsible for the shape and structure of each delta. Many of the world's great rivers have created massive deltas, each with its own peculiarities and typically more complex than the one illustrated in Figure 13.27. Not all rivers have deltas. A river that transports a large sediment load may lack a delta because ocean waves and powerful currents quickly redistribute the material soon after it is deposited. The Columbia River in the Pacific Northwest is an example. In other cases, rivers do not carry sufficient quantities of sediment to build a delta. The St. Lawrence River, for example, has little opportunity to pick up much sediment between its head in Lake Ontario and its mouth in the Gulf of St. Lawrence. The Mississippi River Delta. The Mississippi River Delta resulted from the accumulation of huge quantities of sediment derived from the vast region drained by the river and its tributaries. New Orleans currently rests where there was once ocean. History and structure. The portion of the Mississippi Delta that has formed during the past 6,000 years is shown in Figure 13.28. As the figure illustrates, the delta is actually a series of 7 coalescing subdeltas. Each subdelta formed when the main flow was diverted from one channel to a shorter, more direct path to the Gulf of Mexico. The individual subdeltas intertwine and partially cover each other to produce a complex structure. It is also apparent from Figure 13.28 that after each channel was abandoned, coastal erosion modified the newly formed subdelta. The present subdelta, called a birdfoot delta because of the configuration of its distributaries, has been built by the Mississippi River over the past 500 years. During the past 6,000 years, the river has built a series of 7 coalescing subdeltas. The numbers indicate the order in which the subdeltas were deposited. The present birdfoot delta represents the activity of the past 500 years. The left inset shows the point where the Mississippi may sometime break through and the shorter path it would take to the Gulf of Mexico. Figure 13.28 Growth of the Mississippi River Delta. At present, this active birdfoot delta has extended seaward almost as far as natural forces will allow. In fact, for many years the river has been struggling to cut through a narrow neck of land and shift its course to the Atchafalaya River. If this were to happen, the Mississippi would abandon the lowermost 500 kilometers of its channel in favor of the Atchafalaya's much shorter, 225-kilometer route to the Gulf. In a concerted effort to keep the Mississippi on its present course, a dam-like structure was erected at the site where the channel was trying to break through. A flood in 1973 weakened the control structure, and the river again threatened to shift. This event caused the U.S. Army Corps of Engineers to construct a massive auxiliary dam that was completed in the mid-1980s. For the time being, at least, the inevitable has been avoided, and the Mississippi River continues to flow past Baton Rouge and New Orleans on its way to the Gulf of Mexico. Vanishing wetlands. The delta of the Mississippi River in Louisiana is a biologically significant region that includes about 12,000 square kilometers of coastal wetlands, 40% of all coastal wetlands in the contiguous United States. These flat areas that are only slightly above sea level are sheltered from the wave action of hurricanes and winter storms by low-lying, offshore barrier islands. Both the wetlands and offshore islands were formed and maintained by sediments carried to the Gulf of Mexico by the Mississippi River. These low-lying, sediment-starved swamps, marshes, and bayous are disappearing at an alarming rate. Smart Figure 13.29 Coastal Wetlands. The coastal wetlands of Louisiana are disappearing at an alarming rate, accounting for 80% of the wetland loss in the lower 48 states. According to the U.S. Geological Survey, Louisiana has lost more than 5,000 square kilometers of coastal land since the early 1930s. If wetland loss continues at this rate, another 3,000 square kilometers will vanish by the year 2050. Why is this occurring? Before Europeans settled the delta, the Mississippi River regularly overflowed its banks in seasonal floods. Huge quantities of sediment were deposited atop the delta, which kept the land elevated above sea level. However, with settlement came flood control efforts and the desire to maintain and improve navigation on the river. Artificial levees were constructed to contain the rising river during flood stage. Over time, the levees were extended all the way to the mouth of the Mississippi to keep the channel open to navigation. Watch Mobile Field Trip, Mississippi River Delta. The effects have been straightforward. The levees prevent sediment from being dispersed onto the wetlands. As a result, sediment is not added in sufficient quantities to offset compaction, subsidence, and wave erosion. Thus, the size of the delta and the extent of the wetlands are shrinking. The problem has been exacerbated by a decline in the sediment load of the Mississippi, which has decreased approximately 50% over the past 100 years. A substantial portion of the reduction is due to sediment being trapped upstream by dams on the river's many tributaries. Natural levees. Meandering rivers that occupy valleys with broad floodplains tend to build natural levees that parallel their channels on both banks. Natural levees are built by years of successive floods. When a stream overflows onto the floodplain, the water flows over the surface as a broad sheet. Because flow velocity drops rapidly, the coarser portion of the suspended load is immediately deposited adjacent to the channel. As the water spreads across the floodplain, a thin layer of fine sediment is laid down over the valley floor. This uneven distribution of material produces the gentle, almost imperceptible, slope of the natural levee. These gently sloping structures that parallel a river channel are created by repeated floods. Because the ground next to the channel is higher than the adjacent floodplain, backswamps and Yazoo tributaries may develop. Smart Figure 13.30 Formation of a natural levee. Smart Figure 13.30 Full alternative text description. The natural levees of the lower Mississippi River rise 6 meters above the adjacent valley floor. The area behind a levee is characteristically poorly drained for the obvious reason that water cannot flow over the levee and into the river. Marshes called backswamps often result. When a tributary stream enters a river valley that has a substantial natural levee, it often flows for many kilometers through the backswamps before finding an opening where it enters the main river. Such streams are called Yazoo tributaries, after the Yazoo River, which parallels the lower Mississippi River for more than 300 kilometers. Watch animation, natural levee development with flooding. Alluvial fans. Alluvial fans are fan-shaped deposits that accumulate along steep mountain fronts. When a mountain stream emerges onto a relatively flat lowland, its gradient drops, and it deposits a large portion of its sediment load. Although alluvial fans are more prevalent in arid climates, they are occasionally found in humid regions. Mountain streams, because of their steep gradients, carry much of their sediment load as coarse sand and gravel. Because alluvial fans are composed of these same coarse materials, water that flows across them readily soaks in. When a stream emerges from its valley onto an alluvial fan, its flow divides itself into several distributary channels. The fan shape is produced because the main flow swings back and forth between the distributaries from a fixed point, where the stream exits the mountain. Between rainy periods in deserts, little or no water flows across an alluvial fan, which is evident in the many dry channels that cross its surface. Thus, fans in dry regions grow intermittently, receiving considerable water and sediment only during wet periods. Steep canyons in dry regions are prime locations for debris flows. Therefore, as would be expected, many alluvial fans have debris flow deposits interbedded with the coarse alluvium. Concept checks 13.7. 1. Sketch a cross-section of a simple delta and distinguish among the 3 types of beds that compose it. 2. Explain why the Mississippi Delta consists of 7 coalescing subdeltas. 3. Briefly describe the formation of a natural levee. How is this feature related to backswamps and Yazoo tributaries? 4. Describe the formation of an alluvial fan. 13.8 Floods and flood control. Summarize the various categories of floods and the common measures of flood control. Floods are part of the natural behavior of a stream and occur when the flow of a stream becomes so great that it exceeds the capacity of its channel and overflows its banks. Although floods are natural phenomena, the magnitude and frequency of flooding is often significantly influenced by human activities such as clearing forests and building cities. The occurrence of floods is often linked to other natural hazards, including severe storms and mass wasting processes such as debris flows. Types of floods. Most floods are caused by atmospheric processes that can vary greatly in both time and space. An hour or less of intense thunderstorm rainfall can trigger flash floods in small valleys. By contrast, major floods in large river valleys often result from an extraordinary series of precipitation events over a broad region, for many days or weeks. Common flood types include regional floods, flash floods, ice jam floods, and dam failure floods. Regional floods. Most regional floods are seasonal. Rapid melting of snow in spring and/or heavy spring rains often overwhelm rivers. For example, the extensive 1997 flood along the Red River in North Dakota was preceded by an especially snowy winter and an early spring blizzard. Early April brought rapidly rising temperatures, melting the snow in a matter of days and causing a record-breaking 500-year flood. Roughly 4.5 million acres were underwater, and the losses in the Grand Forks, North Dakota, region exceeded $3.5 billion. Ice jams also contribute to floods on the Red River of the North. See the section Ice Jam Floods. In April 2011, unrelenting storms brought record rains to the Mississippi watershed. The Ohio Valley, which makes up the eastern portion of the Mississippi's drainage basin, received nearly 300% of its normal springtime precipitation. When that rainfall combined with water from the past winter's large and extensive, rapidly melting snowpack, the Mississippi River and many of its tributaries began to swell to record levels by early May. The resulting floods were among the largest and most damaging in nearly a century. Like most other regional floods, these were associated with weather phenomena that could be forecast with a good deal of accuracy. This allowed adequate time to warn and evacuate thousands of people who were in harm's way. Although economic losses approached $4 billion, loss of life was small. Flash floods. Unlike extensive regional floods, flash floods are more limited in extent. Flash floods occur with little warning and can be deadly because they produce a rapid rise in water levels and can have a devastating flow velocity. Several factors influence flash flooding. Among them are rainfall intensity and duration, surface conditions, and topography. Urban areas are susceptible to flash floods because a high percentage of the surface area is composed of impervious roofs, streets, and parking lots, where runoff is very rapid. Mountainous areas are susceptible because steep slopes can quickly funnel runoff into narrow canyons. Figure 13.31 Floods are dangerous natural hazards. Although short-lived, flash floods can be powerful and often occur with little advance warning. The event shown here occurred in an urban setting. In most years, floods are responsible for the greatest number of storm-related deaths. The average number of hurricane deaths was dramatically affected by Hurricane Katrina. For all other years on this graph, hurricane fatalities numbered fewer than 20. Figure 13.32 Effect of urban development on flooding. Streamflow in Mercer Creek, an urban stream in western Washington, increased more quickly, reached a higher peak discharge, and had a larger volume during a one-day storm on February 1, 2000, than streamflow in Newaukum Creek, a nearby rural stream. Streamflow during the following week, however, was greater in Newaukum Creek. Figure 13.32 Full alternative text description. Did you know? Just 6 in of fast-moving water can knock a person down. Many cars will float and be swept away in only 2 feet of water. More than half of all U.S. flash flood fatalities are automobile-related. Ice jam floods. Frozen rivers are especially susceptible to ice jam floods. As the level of a stream rises, it breaks up ice and creates ice flows that can accumulate on channel obstructions. Jams of this nature create temporary ice dams across the channel. Water trapped upstream can rise rapidly and overflow the channel banks. When an ice dam fails, water behind the dam is often released with sufficient force to inflict considerable damage downstream. These floods are often associated with northward flowing rivers in the northern hemisphere. The Red River of the North, mentioned earlier, is an example. Siberia has several northward flowing rivers, including the Ob, Lena, and Yenisei, that frequently experience these floods. When spring arrives, ice melts in the warmer southern portions of a river and its drainage basin, while farther north the river remains frozen. Water flowing from the south backs up behind the frozen northern portion of the river. Dam failure floods. Human interference with stream systems can cause floods. A prime example is the failure of a dam or an artificial levee designed to contain small or moderate floods. When larger floods occur, the dam or levee may fail, resulting in the water behind it being released as a flash flood. The bursting of a dam in 1889 on the Little Conemaugh River caused the devastating Johnstown, Pennsylvania, flood that took more than 2,200 lives. Flood control. Several strategies have been devised to eliminate or lessen the catastrophic impact of floods on our lives and the environment. Engineering efforts include the construction of artificial levees, river channelization, and the building of flood control dams. Artificial levees. Artificial levees are earthen mounds built on river banks to increase the volume of water the channel can hold. Levees, used since ancient times, are the most commonly used stream containment structures. In some locations, concrete flood walls are constructed to function as artificial levees. Many artificial levees were not built to withstand periods of extreme flooding. For example, numerous levees failed during the summer of 1993, when the upper Mississippi and many of its tributaries experienced record flooding. During that event, flood walls at St. Louis, Missouri, created a bottleneck for the river that led to increased flooding upstream of the city. Channelization. Channelization involves altering a stream channel in order to make the flow more efficient. This may simply involve clearing a channel of obstructions or dredging a channel to make it wider and deeper. A more radical alteration involves straightening a channel by creating artificial cutoffs. The idea is that by shortening the stream, the gradient and hence the flow velocity are increased. By increasing velocity, the larger discharge associated with flooding can be dispersed more rapidly. Beginning in the early 1930s, the U.S. Army Corps of Engineers created many artificial cutoffs on the Mississippi for the purpose of increasing the efficiency of the channel and reducing the threat of flooding. In all, the river was shortened more than 240 kilometers. The program has been somewhat successful in reducing the height of the river in flood stage. However, because the river's tendency toward meandering still exists, preventing the river from returning to its previous course has been difficult. Flood control dams. Flood control dams are built to store floodwater and then release it slowly, in a controlled manner. Since the 1920s, thousands of dams have been built on rivers. Nearly every major river in the United States has at least one dam. Many dams have significant non-flood-related functions, such as providing water for irrigated agriculture and for hydroelectric power generation. Many reservoirs are also major regional recreational facilities. Dams are often built to control flooding. Dams and their reservoirs also provide recreational opportunities and water for irrigation and hydroelectric power generation. As the graph shows, hydropower is a major form of renewable energy. The graph shows U.S. energy consumption in 2014. Smart Figure 13.33 dams have multiple functions. Smart Figure 13.33 Full alternative text description. Although dams are effective in reducing flooding and provide other benefits, their construction and maintenance also have significant costs and consequences. For example, reservoirs created by dams may cover valuable farmland, forests, historic sites, and scenic valleys. Large dams can also cause significant damage to river ecosystems that have developed over thousands of years. Watch tutorial, Renewable Energy. Furthermore, building dams is not a permanent solution to flooding. Sedimentation behind a dam gradually diminishes the volume of its reservoir, reducing the long-term effectiveness of this flood control measure. Did you know? Urban development increases runoff. As a result, peak discharge and flood frequency increase in urban areas. Humans have covered an amazing amount of land with buildings, parking lots, and roads. A recent study indicated that the area of such impervious surfaces in the United States amounts to more than nearly 44,000 miles, which is slightly less than the area of the state of Ohio. A non-structural approach. All the flood control measures described so far employ structural solutions to control rivers. These solutions are typically expensive and often give those who reside on the floodplain a false sense of security. Many scientists and engineers advocate a non-structural approach to flood control. They suggest that sound floodplain management is an alternative to artificial levees, dams, and channelization. By identifying high-risk flood areas, appropriate zoning regulations can be implemented to minimize development and promote safer, more appropriate land use. Concept checks 13.8. 1. List and distinguish among 4 types of floods. 2. Describe 3 basic flood control strategies. What are some drawbacks of each? 3. What is meant by a non-structural approach to flood control? Concepts in review, running water. 13.1 Earth as a system, the hydrologic cycle. List the hydrosphere's major reservoirs and describe the different paths that water takes through the hydrologic cycle. Key terms. Hydrologic cycle: evaporation, infiltration, runoff, transpiration, evapotranspiration. Water moves through the hydrosphere's different reservoirs by evaporating, condensing into clouds, and falling as precipitation. Once it reaches the ground surface, rain can either soak into the soil, evaporate, be returned to the atmosphere by plant transpiration, or run off over the surface. At any given time, running water represents a small fraction of the total water on Earth. Nevertheless, huge quantities are cycled through this part of the hydrologic system, making running water the most important erosional agent sculpting Earth's surface. 13.2 Running water. Describe the nature of drainage basins and river systems. Sketch and briefly explain 4 basic drainage patterns. Key terms. Stream, river. Drainage basin, divide. Headward erosion, dendritic pattern, radial pattern. Rectangular pattern, trellis pattern, water gap, superposed stream. The land area that contributes water to a stream is its drainage basin. Drainage basins are separated by imaginary lines called divides. River systems tend to erode at the upstream end, transport sediment through the middle section, and deposit sediment at the downstream end. A stream effectively erodes in a headward direction, thereby lengthening its course. A water gap is a steep-walled notch through which a stream flows. Water gaps are often associated with superposed streams. Identify each of the drainage patterns depicted in the accompanying sketch. Figure 13.10 to 1 full alternative text description. 13.3 Streamflow characteristics. Discuss streamflow and the factors that cause it to change. Key terms. Laminar flow, turbulent flow, gradient, wetted perimeter, discharge, longitudinal profile, head, mouth. The flow of water in a stream may be laminar or turbulent. A stream's flow velocity is influenced by channel gradient, size, shape, and roughness of the channel, and discharge. A cross-sectional view of a stream from head to mouth is a longitudinal profile. Usually, the gradient and roughness of the stream channel decrease going downstream, whereas the size of the channel, stream discharge, and flow velocity increase in the downstream direction. Sketch a typical longitudinal profile. Where does most erosion happen? Where is sediment transport the dominant process? 13. For the work of running water. Outline the ways in which streams erode, transport, and deposit sediment. Key terms. Quarrying abrasion pothole corrosion dissolved load suspended load bed load settling velocity saltation capacity competence. Sorting alluvium. Streams are powerful agents of erosion that carve solid rock through quarrying, abrasion, and the focused drilling that results in potholes. Turbulent water also lifts loose particles from the stream bed. In areas of soluble bedrock such as limestone, stream water can also corrode the landscape by dissolving the rock. Sediment is